So thank you very much for the very nice workshop. So I really enjoy the crossroad of topics that we can see today. So I will talk mostly about physical interaction, which is for me the most core of physical AI, because we need to master contacts if we want to move forward and to make real motion and real achievements. I mean, you all know, but robotics is a very multidisciplinary field with hardware. So I would just talk briefly about hardware, but we never mentioned software hardware in this workshop. But I think this is the most important track that we need to focus on now, aligned with the software perspective. And so for the software perspective, we can see perception, optimization, machine learning, and control. And now with foundation model, we are trying to glue everything together. But at least there is still a gap between software and hardware, and we should move forward. So I would just like to cover a bit, from my perspective, where do we stand in robotics today? So as we mentioned, robots are first and foremost physical systems, and so we should first focus on good hardware to make good motion. And I think all the people that are now at the cutting edge research in robotics, like Toyota Research Institute or Boston Dynamics or Unity, this is first because they have a very good hardware that they master and on which they can rely. And so just a short story. This is a story I think most of you already know, but I don't know if you know which is behind this robot. Maybe. So yeah, Mark Robot, exactly. So we saw in the 80s at MIT, a very nice but simple robot, but very dynamic. So for me, when I'm teaching robotics at ENS, I'm always starting the class with this robot, because I think this is a fundamental thing, because behind there is very few control, a very nice design, and which makes the things already working and operating with a very limited amount of computational power. So this is Mark Ebert's academic journey, and then he started Boston Dynamics. This is in acceleration, but this is a Petman robot. Then we have Atlas #1 during the DARPA Robotics Challenge. Then we have Atlas #2, still hydraulic robot. So Petman, Atlas #1, Atlas #2 were the hydraulic robot. We have seen very fantastic videos from Boston Dynamics, and with a lot of gag videos at the end showing what was failing, which is very nice, I think. And many companies today are still not showing what is not working, and I think this is very important to show. And I think the work that LBM teams did is very nice in this avenue. And then we have the last version of the Atlas, so number 3, line 3 robot, which is a fully electrical robot. So what we don't see here is that there was a maturation of the technology to build robots, and with what we call quasi-direct drive solutions, in such a way that we reduce the dissipation of power inside the transmission of the robot. So just to mention that. So I think for the history of Boston Dynamics, you can see the evolution of robotics, and I think this is important to have in mind if we want to understand what happens, not only at the software perspective, but also at the hardware perspective. So we are in the Willow team, so we are not doing robots, making robots. It's a very dedicated and complex task, but we are mostly working on the software perspective, and I will try to cover a bit part of this story today. So again, where do we stand today from a software perspective? So I think we have great success of robotics for manufacturing and mobile robotics, but as soon as we want to put robots outside of laboratories or plants, this is a failure, and we still are lacking from autonomous robots. And this is a picture from the DARPA Robotics Challenge, which is less valid today because we can see very impressive video from many companies over the world, but we are still at this level. And for me, the main challenge of physical AI is trying to embrace rich and complex physical interaction in a changing world. And I think this is one of the purposes of why we are here today, to discuss about spatial AI and physical AI, and the main problem of understanding contact and trying to master physical contact interaction. So, the modern way of controlling robots, I will cover briefly what Nicolas presented just before. And this is, I'm coming from the same school of spirit, so this is why I think there is some redundancy. But the idea that we have a physical space in which the robot evolves, we have sensorial space, which is just a projection of physical space, and with limited amount of information, and we need to have prior knowledge to rebuild the state of the robot. And then from this sensorial space, we try to to take decisions to move, to control the robots, the motor of the robots, and to move forward. And where we play a game when we do software engineering for robotics is to build a control policy. And so this control policy is just mapping between sensorial information and control outputs. Okay, so what we have seen before in the presentation of Nikolai, that we have on one side optimal control, which is a very old control theory coming back from the 50s. So I just plot the figure of Leys, Pontrier-Green, and the idea that in the continuous time, we want to minimize the cost function over a given horizon according to system dynamics, which is assumed to be none, and according to some given non-state. And behind that, we have LQR methods, which is a very classic approach when we have a linear dynamics, or Kalman filtering if we want to do optimal estimation for a linear system. And this is working, and this is how, for instance, we send rockets in the space by using this theory, and this is nice. Nowadays, I mean, we are much more and more talking about policy learning with RL, which is one of the key component of policy learning. And so the idea is, instead of working along a single trajectory, what you try to do is to learn a mapping from which is operating for the world safe space. And the good thing is that you can put some distribution over your unknowns in such a way that you can be robust. And today, I mean, with deep reinforcement learning, what is very nice is also that you can map very complex sensorial inputs to control outputs in such a way that you are able to learn complex control laws. And this is, of course, Richard Bellman, which is one of the fathers of this theory. So often we mention that RL is model free, but today we use massively data generated from a simulator which contain a model. So I would say that this is also a model-based solutions, even if and the thing that we are not exploiting so much information that we can extract from the simulators as a privileged knowledge in order to accelerate the learning, for instance, of a control policy. And this is one of the topics that we are trying to cover in the Willow team. So in terms of success story, I think optimal control remains a very nice paradigm for Boston Dynamics, and they are using the online version, which is MPC, so model predictive control, which is working very well. And on the other side, I mean, the big success story that I've shown for the first time RL being deployed on the real system is, of course, the work by the team of Marco Hutter at ETH Zurich, which is nicely showing that we can learn a control stabilizer for the robots in such a way that we are able to embrace the world with all the uncertainties that we can get from a rich and unknown environment. So when I see this problem, what I see is optimization, of course. So either it's just what we call trajectory optimization, and this is often tractable, but it lacks of robustness. And on the other side, we have policy learning, which is also another kind of optimal control of optimization problem, where we often use stochastic gradient descent. It's often more robust against uncertainties, but we are also subject to the curse of dimensionality. So currently, we are, building massive clusters for this curse of dimensionality effect. But the question is, can we try to lower this burden in general by trying to have better solutions for solving problems? And then we have, of course, the third approach, which is now emerging. I think this is, normally I show the picture of physical intelligence, but today I took the one from Toyota Research Institute. I think this is a very impressive work that people are making. I'm very not jealous, but I think it's a good time today to try to see the convergence of model-based and database-driven approach for robotics and trying to do that. And I really enjoyed your talk, by the way, Adrien. And so we discussed a lot with Ross Tedrek more than 1 year ago at RSS in Delft, and he was saying something which I think is very important. So behind this single author, in fact, it's a team, a big team, and I think this is very impressive. We never succeeded to make it happen in robotics, to have so large amount of people working together to solve a problem. And I would just take the word of Tedrek, of Ross Tedrek, is saying big science. I think today we are changing a paradigm, going towards big science for robotics, like people did, for instance, for physics. So the question, which institution in the world can embrace this kind of big science? Currently, in Europe, I don't see an institution which is able to scale like companies like Toyota, which is doing that, but with a large effort of Ross Tedrek and colleagues to convince people to invest in this kind of paradigm, and we can see many other companies. But the question is, can we do? Can we do that in academia? I don't think so, but we can try to build the foundations, so mathematical foundations, which can help to reduce at least the computational burden of all these solutions, which are very data hungry and computationally hungry. So I also want to come to the solutions to the need of data. So will data solve robotics and automation in general? I will just take a step back from some sentence from Bernard Espio. So some people, at least grown-up people knows him because he was a big figure in robotics in Grenoble. He was also a big figure in robotics in general in the world because he's the guy behind the task function approach. So maybe some of you know, but it's a very nice concept in control theory for driving robots. And he has been also working a lot on perception for robotics. And so in 2012, he was mentioning that there was two schools of thought, and both are deficient. So one approach is to model the external world, but not everything can be modeled. And the other approach is learning, but what is learned is so far too basic and time-consuming. So it seems to him at this time that the autonomy of humanoid robots would come from the combination of these two approaches. So it was at the time of AlexNet and all these things. So today, what we have seen today from the talk of Adrien is that we are at the right time to have the combination of data-driven and maybe model-based to drive the motion of robots, maybe not yet locomotion for humanoid robots, but at least manipulation, and which is the next big challenge. And so, yeah, this is some sentence. And again, when I teach robotics at ENS, I take this sentence because I think it's important to recover the thought from the past, which are still valid today and that people were already aware at this time. Another thing that we need to also think, I think what is nice now is to discuss about big models versus big data. And I think, if you want to have a nice overview from a leading researcher in the world, I think it is a nice discussions and outputs from many researchers coming from different perspectives. So I think everybody knows all these names, big names, and I think there is not a joint consensus, but things are moving, and we can build something around this discussion together. So the question is, to what extent can robotics foundation model scale with increased amount of data? And I think the LBM team is trying also to answer this question with a very nice evaluation program, and I think this is something that we need and have to follow, but with limited resources. So what we can see today is that we have more and more massive data sets available, but not maybe at the scale of Toyota or Physical Intelligence and other RGBot companies, for instance. So just for me, from my perspective, all models are wrong, and this is of course true. But there are good physical priors for learning control policy from curated and limited data. And so we need to inject this kind of prior knowledge if we want to lower at some points the computational burden and the need of data. So I will briefly show you what we are doing in Willow in terms of robotic and AI. So just to say that Willow is mostly known because it's a computer vision team at the beginning, and now we switch a bit part of the team to do robotics and AI, so perception, learning, simulation, and control together, and we are trying to embrace all these topics together. So this is Willow and Sierra. So maybe Sierra team is less known for people here, but it's a team from Francis Bach, which is very known for in machine learning and optimization. And so we are very, in a nice mood at Inria Paris, working together on the same floor and trying to have a nice discussion, exchanges about the thing. So the team of Francis is very theoretical, but very inspiring for us to try to put much more theory inside what we are doing in robotics. So the team is growing. So now we are almost 50. So there is Cordelia today and other people. So we have many postdocs and also many engineers, which is not classic for an academic team, at least in France, because we build a lot of software. And I think like Pinocchio, and I will try to cover it, but I think it's important for us to build software on which we can trust, on which we can make research, and that we can also deliver to the rest of the community for building larger applications. So if we need to summarize the modern control paradigm today is data, optimization, and compute. So data, if we take the presentation from Adrien is a lot of supervised learning from human data. Optimization is often zero orders optimizations, which is slow to converge. And we need a larger amount of compute. So we never mentioned these numbers, but we need dedicated infrastructure for that. So huge, slow, and massive. And so maybe one program that I want to pursue over the next few years is try to work mostly around a much more weakly supervised manner for reducing the amount of data, trying to accelerate convergence of optimization solvers, and also trying to work around low complexity algorithms. So I will show you in this talk how we have been able to reduce the computational burden of simulation drastically. So key ingredients, so reliable data, good optimization, and reasonable compute. This is, the motto of the team. So in the team, we are trying to cover perception, optimization, machine learning, and control together. And our vision is to advance these research topics together with, as I mentioned, building reliable software for robotics and beyond, because in fact, what we can do in robotics can also have impact in other domains. So this is something that I just mentioned. But for me, something which is important if we want to connect model-based and database is gradient information for instance, architecture and so on. So it's important to work around this notion of gradients, to connect model-based, which is one way to connect first principle, inductive bias, and interpretability guarantees to database, which are the way to go if we want to deploy things in the real world. So another paradigm, I think, a research agenda which is true for academia, but less maybe for companies, is to transform black box into gray and maybe white box, I don't know. But at least trying to see something behind the notion of architecture. And so in the team, we have started also to work with robots. So we have a large span of robots, and we want to build a single software pipeline in such a way that we can work on manipulation, local manipulation, and locomotion in general of a generic platform. Okay, so today we were several of the team today. So Cordelia presented, she's here, and we have posters. So maybe one poster was about Sobolev diffusion policy, very inspired by the work of Toyota and Rustedrek team about how we can accelerate diffusion policy learning using gradients, which is something interesting, I think, to lower the need of computational power. And another work, I think, also promising. So we have been discussing with Christian about off policy. And I think this is some work from the students of the team to try to leverage, to learn both actor and critic using flow policy and distillation of flow policy into actor in such a way that we are able to extract the most sensitive information from dataset in the context of poor dataset. And so, this is some benchmarks that they did, but this is, in green, this is our method which achieve currently state-of-the-art performances for off policy using a soon combination of energy-based and flow matching-based solution. So in the team also, what we see that open source can be used as a catalyst. So I will try to cover the research agenda that we have and results for the software that we developed. And the paradigm that we are trying to follow, unlike others, I think it's more with less, trying to go towards simpler, nimbler, faster, stronger solutions with less code, compute, and bugs in general. So I started to develop that when I was in Toulouse, in the Gepetto team called Pinocchio. So Pinocchio is implementing mostly rigid body dynamics algorithm to control robots in general and any kind of rigid robots. So today is very used by many companies around the world and in France. So Wondercraft, which is the building exoskeleton, Enchanted Tools. But if you have a Franca Amica now, they provide Pinocchio inside them and so on. So many companies are now relying on Pinocchio. So we are very proud of these achievements. Many humanoid robots today are also driven by Pinocchio, so which is also a nice success, I think, from academia, showing that what we can produce as a software can be used by companies. So not all of them, of course, but some of them. So we don't know for all of them, I would say, but at least Unitary we know. So we have also been working on the perception aspect. So this was the work of Yann Labé in the team, and with a joint collaboration with Dieter Fox's team at NVIDIA. And Joseph Sivic. This is a kind of application of object pose estimations, 6-digit estimations, like this one, which is a nice illustration of where you can try to use 6-digit estimation in for real-world application. So this is a very nice work by Boston Dynamics. In the team, we work also a lot of optimization. So for us, optimization is key. And for that, if you look at this motion, this is optimization based. There is no RL. This was done more than 10 years ago by Honda, which is a very nice achievement of locomotion on a biped robot, very smooth motion. So behind that, you have optimization. So optimization remains ubiquitous in robotics. And often, what you can see that there is a lot of optimizers that you can download on the internet that you can try to use on robots, but they won't work because they are not reliable enough. So they cannot find solution for problem, and it can be a very nightmare if you want to do online control. And also, they might be too slow to be deployed on a real robot. So for that, we are trying to build dedicated solvers for robotics. And so, for instance, we have developed over the past 3 years ProgSuite, which is a nice library for solving QPs, quadratic programming problems, which are ubiquitous in robotics. And now we are trying to extend it towards non-smooth and non-convex optimization problems. So this is a very long agenda in terms of optimization, but we will see later some result of this aspect for generating locomotion problem. So what is nice is that even if you are a roboticist, we can try to also to do some benchmarks against some problems of the literature, and we can also beat commercial solver in terms of timing, efficiency, and so on by writing our own solver, and this is also a nice achievement. So what we do in general is that we devise new optimization schemes which are new in terms of theory, and solvers that promote scalability, stability, efficiency, and differentiability. One key thing is that we are trying to do also differentiable optimization if we want to put optimization layer inside deep learning, for instance. And what you want when you do differentiable optimization is that your solver always send you a solution, even if there is no solution. You don't want, when you do a forward pass over your neural architecture, to have a NAND somewhere or no solution. And so for that, we develop solvers which are able to always send a solution, which is the closest one if the problem is infeasible. And this is a very nice feature for differentiability. So another stuff on which we work a lot and we have been pushing a lot of efforts is simulation. So I will cover that, and I really enjoy also the talk of Adrien again. So again, Adrien, but just because he mentioned that simulation remains key, and I think it's encouraging us to pursue all the work around simulation. I know that the LBM team is also working a lot around Drake, and Drake is also pursuing a lot of efforts on the rich contact scenarios and simulation. And I think what they are doing is very nice. And just to mention that there is only few people, in fact, in the remaining that still are working on this topic, which remains central to robotics. And I encourage young generation, if they want, to work on this topic, because I think it remains fundamental. Even if today we are speaking about world model, which is also another line of simulation in some sense, we still need, at some point, model-based simulation if we want to understand things. So what we want to do is advancing simulation efficiency and reliability, and how do we manage to break the simulation problem. So what I mean by breaking simulation problem is to lower the complexity of simulation in general. So as you have seen, so simulation is ubiquitous in robotics. So I think this demonstration, I think this is simulation on the top right. So it's still relying on simulation to assess, to certify the motion and to check that the motion there is no collision, which is a nice feature, a last line feature. And this is another example of using simulators. This is the data, often it's data hungry application when you do RL, but this is some timings that you can find in the Dickstream paper by NVIDIA is that for each training it's 60 hours of training with 16 kilos environment, which is huge. So 10 power 11 calls to the simulator, which is huge. 55 years of simulation, which is huge. $1,000 for doing one single training, which is a bit huge, and which correspond to some carbon footprint in terms of carbon emission with a car, and which has an impact. So all the time that you call a cluster to do a computation, it has an impact somewhere, and this is not free. And I think at some point we will have to pay the price of this kind of things. So the vision that we have is trying to drastically lower the computational burden of simulation. And again, with the same wording, so scalability, efficiency, robustness, and differentiability. So simulation is mostly 3 main stages. So the first one is about collision detection. You want to find the contact points between the objects that you are in your environment and between them. Then you have collision resolution, is how you compute the contact forces, which are inherent to the physics of the world. And then time integration, because what you do is that you numerically discretize an ordinary differential equation to try to simulate it, and which is hard to simulate in general. So collision detection, if you have n object in your scene, you need to do n² query to your system to check collision between a pair of geometry. And so this is called, so you have broad phase, narrow phase to try to lower this burden. And the main algorithm which is known from the literature is the JDK algorithm. So I don't know if you know him, but Gilbert Johnson Kerty, which has been developed in the 80s to solve collision problems in a very few amount of microseconds in general. So even for very large meshes. So the idea of collision detection is that you want to find the contact point between geometries, or what we call the witness point. And often we assume that the geometry are convex. And so instead of working in the space of the ambient space of the geometry, you work in the with the Minkowski difference, which is a way to try to solve what we call a minimum point problem, which is often easier to solve than the original problem. So this work has been developed in the 80s, as mentioned, by these 3 guys. And for 40 years, nobody has tried, or at least had succeeded to reduce the potential burden of this algorithm. And what you can do and what you can think is that, in fact, collision detection at this time was seen as a computational geometry problem. So it means without thinking of optimization, because it was not, communities were not discussing so much between together. But what you can see is that, in fact, JDK algorithm, I won't cover it directly, but it's a gradient descent mechanism, what we call the Frank-Wolf algorithm. And you can try, in fact, to use accelerated gradient descents to try to reduce the number of iterations that you need to solve this optimization problem. And this is working pretty well because we can divide by 2 the number of iterations that you need to converge. And this has a drastic impact because you divide by your timings by 2. And so as you have n² queries to your local collision checker, you have an impact. And this is something that we have put, you have on the left the paper. We have forked, like Toyota did, FCL, the flexible fast collision detection library by Dinesh Manosha, and we have pursued the work of developing it. And now we are maintaining a fork of it. And what we have been able to do is that we have been able to recast collision detection as a Frank-Wolf optimization procedure to accelerate it. And just to mention that if you have implemented JDK, which is in any video games, for instance, there is JDK which is running, you just need to change 2 lines of code to get the benefits out of that. So it means that you don't need to rewrite a new software stack. You just need to change 2 lines of code. And this is very magic. And this has been done only 40 years after the creation of the algorithm. But I think there is many algorithms in the literature that we can still accelerate and make huge progress and huge impact for the community. So collision resolution. So the idea is that we need to understand how simulator works. And for that, with Cordelia and Quentin, which was our PhD students, we have been working a lot on trying to understand contact models in robotics. So, and because in fact, there is no ideal simulator. All the simulators are cheating in some way, and this is normal or expected at some point because the problem is very hard. So what we did in this thing is that we have tried to cover all the main simulators like Bullet, Module Code, Drake, Racing, and so on, and try to see the limitation of each of them and trying to have a fair analysis of what happens in terms of physical inaccuracy and inexactness that can be exploited by your RL algorithm if you do deep RL, for instance, because you will exploit them for sure. So what we observe is that modern simulators tend to drastically simplify or relax physics at the price of physical inconsistency and accuracy. So what is contact physics? Physics of contacts is mostly you have a contact point between 2 geometries, and what you can define is that you have 3 main stages, 3 different modes, sorry. breaking, sticking, and sliding. So either you are trying to remove your tip from the table, and so you have a positive velocity and zero forces. Either you are sticking, so it means that you have a zero velocity at the contact point, and the contact forces lie in the so-called Coulomb friction cone. And third, what we have is a sliding mode, which is corresponding to the fact that when you start to saturate your friction cone, you start to slide on the surface. And this is another phenomenon which is very important to capture. And this corresponds to what we call a nonlinear complementarity problem, which is hard to solve in general. I won't dive into the math, but what you can show, I mean, what we have shown and demonstrated that you can recast it as an interleave optimization problem that you can solve efficiently with what we call ADMM-based approaches. So this is something that we have developed. I mean, we have presented last year at RSS. We are still making progress on that, and soon you will see better solvers. I cannot mention everything, but just to say that. And another thing that we did, and I think this will change the paradigm of simulation, is that we are making progress on how to solve this linear system. So often, you need to inverse this matrix if you want to solve the problem. Inverting this matrix, the cost is this one. So it's cubic in terms of m is the number of contact points. And what we have found by exploiting the structure of a robotic system, because we have a kinetic structure with a lot of sparsity and so on, we can reach a linear complexity. So it means that you go from cubic to linear complexity. So it means that maybe you don't need really a GPU for making large-scale simulation, or you can do more computation on a single CPU thread to reach the same amount of computation than a GPU. So I think this is something that we need to work on. And so currently, there is no learning. It's just reworking the math, which are behind simulation, and trying to see some tricks and to exploit the problem structure to lower the global complexity. Okay, sorry. So just to say that all the things that we mentioned, so it has been recently reproduced by Disney Research. They did something very aligned with the comparative analysis that we did, but even much more involved, I would say. And they have some nice conclusion about our work, so I won't cover it directly, but they assess that it has a good behavior for the simulation of their complex system. And I don't know, I mean, they're trying to build a really complex robot, much more complex than what Boston Dynamics is doing in terms of numbers of links and number of degrees of freedom. So we double the number of links here, we double the number of degrees of freedom that we need to control. And the idea for them is to deploy this robot inside their main attraction park, at least in Paris, in Disney Paris. So I think, this is a nice, for us, recognition of what we did. So there is also nowadays a trend to go more and more toward GPU-based simulation, which is understandable because we want to have everything, all the computational flow on GPUs. Yet, I don't know if we need to put all our efforts on GPUs, and maybe we can still put our efforts on CPUs, because CPUs is, for me, I prefer to work on my local computer without to have the need for big GPUs. So the good thing with CPU-based simulator is that we can be as fast as possible, but we cannot do massive computations. GPU is very done for massive computation, but you cannot be very fast or as fast as CPU-based. And the ideal simulator will be to go there, so more with less. So in the team, we are now putting also efforts, which are also engineering efforts, to go toward this ideal simulator, saying that we want to do massive computations if we want, but maybe we don't need if we use gradients, and to be also as fast as possible. So a last thing that I want to show you is now if we want to invert the physics. So physics is a complex problem, non-smooth. But what we did recently is that we developed contact implicit inverse dynamics solvers. So inverse dynamics is known from a while. Usama Khatib at Stanford was one of the precursors of that. But at this time, you had to assume the contact mode of each limb that you have in contact. So you need to, if you are sticking, you say that to the solver that you are sticking. Here, what we did is that we put directly the simulator here as a constraint, and we developed a dedicated non-smooth, non-convex solver for that, and which is able to solve this problem in very few milliseconds, just to say, and accurately. and you can define very sparse objective. Sparse objective in the sense that if you want to ask your robot to just jump, you just mention that you want to jump at a given altitude. And this is the very sparse information that you provide to a solver. And what we have been able to do is to have an automatic way of reasoning about contact creation and breaking via non-convex and non-smooth optimization. And this is some result that we can show. So this is real time, no learning. And this is the kind of motion which is often you need trajectory optimization to solve it. Here, there is no preview in the future. It's just what we call instantaneous control. So the robot just foresees one step in advance, and he's able to find a nice strategy, which is very myopic in terms of preview, but which is very similar to what Nicolas presented just before. So, but before it was using RL, massive computation and so on. This is milliseconds on your computer, laptop, single thread, and so on. And just by inverting the physics, but the key things here is really to solve properly the optimization problem. Often, what we do in robotics is we try to relax the problem, to make it solvable by your dedicated solvers. But in fact, it's not a good thing that to relax the problem. We can exploit the structure of the problem and trying to devise dedicated optimization scheme which works properly with the problem. And this is what we are trying to do in the team. And we are making progress towards releasing all these achievements inside new software. Okay, so maybe I don't have so much time. Do I have?
Exactly 5 minutes, but maybe 1 or 2 if you could complete 1 or 2 minutes.
Okay, so something that we want to do also is to have differentiable simulators. So Nicolas mentioned that currently there is no good good differentiable simulator, and by doing differentiable simulation, we can connect data to model and model to data, which is a good thing. I won't cover all the things, but as we mentioned, so contact dynamics is non-smooth, which makes the problem very difficult to differentiate. So for instance, you have here a rocket, you don't have any control input, so you don't move. If you put a small control thrust, you won't move either, and so you will start to move when you start to compensate for gravity. So this makes the problem totally non-differentiable, and which is hard to exploit inside classic optimization scheme, which assume smooth gradient. So classic optimization problem solver will fail. And what we have shown is that we can connect optimal control and error throttling for the notion of randomized smoothing. So I don't know if you are aware of randomized smoothing. So it's really related to what Nicolas mentioned previously, MPPI. So randomized smoothing in a way by perturbating with a random perturbation my input data, for instance, for this linear programming problem, I will have an averaging, in fact, of the solution over different vertices, which are optimal solution according to the orientation of my vector theta. And I will do an averaging of this solution, and it will give me a smooth gradient out of a non-smooth problem, because argmin is non-smooth. And so this is called randomized smoothing, and which is a nice solution to get gradient out of that. And what we have shown is that, in fact, optimal control and policy learning, in fact, you can connect them for this notion of randomized smoothing. And this is a parallel result from the team of Roy Cedric at MIT with Teresiu. So the thing is that policy learning, on the right side, what they are doing is zero-order method, which is that we can be slow to converge in general. And on the left side, what we can see is that we can try to do first-order method. So I won't cover this part because I don't have enough time, but just to say that we have provided and developed a nice solution, a nice framework to extract subgradients information out of the differentiable simulation. Subgradients, because we have a non-smooth problem. And we developed, I will just show you timings just to convince you. But so often, if you look at the Mujoko GitHub, in the issue, they will say that if you want to compute derivatives, just use finite differences. If you do that for a non-smooth problem, it will be a drama, because you cannot differentiate using that. So what you need to properly capture the derivative, this is what we have done. And in fact, computing the derivative here, so I will just show you for the Atlas robot. But for doing the forward simulation, it's 100 microseconds for doing one step. But for computing the gradient, it's even less than the forward path of simulation. So what you can do is to get a gradient information for the double price of the forward simulation. Okay, so if you double the timings, you can get also gradient information, and you can use it to plug that, for instance, in policy learning, in trajectory optimization, and so on. And this is a nice result. And for that, we have been able to properly exploit all the features of our robots, design and mechanism. So this is a joint work with Quentin, Louis, and Yann at Inria. So again, so open source for us is important, and it should be a catalyst for transforming research and transferring research from academia to industry. So we have this set of methods that we have been able to develop over the past few years. And we are trying now to launch an initiative called Maestro, trying to build an open source consortium for robotics to catalyze research and deployment in general. So it will be like, we can think of scikit-learn. So Inria is known for scikit-learn, so which has been built around the consortium. So we want to do the same kind of initiative around robotics, and with a set of methods and solvers and software modules for real-world application. So now I'm done. So main lesson, good hardware is essential. Good software is essential too, and I think we need to work on both sides. So not really autonomous robots exist yet, and simulation remains a cornerstone in robotics, and I think we need to pursue some effort on this part, and while we still also work on the other aspect of simulation, which is world models. So this is the Willow Sierra team, and if you are looking for a postdoc engineering position and maybe PhD, we are hiring in the team.